everyone, today I would like to share with you all an interesting mathematical fact which deals with improper integrals that I recently learned and that also has a really nice corollary. But before, let us take a look at the following integral. The integral from negative infinity to positive infinity of 1 over 1 plus x squared with respect to x. So now, to solve this integral, I would like to use a trig substitution, namely, let x equals tangent theta, which means dx will be secant squared theta d theta, and then on our substitution, taking the inverse tangent on both sides, we get theta equals arctan x. But then, if we plug in our bounds into this, we will get, well, as x approaches infinity, arctan x approaches pi over 2, and as x approaches negative infinity, since inverse tangent is an odd function, as x goes to infinity, inverse tangent will approach negative pi over 2 in this case. So now you'll have 1 over 1 plus tangent squared is secant squared is secant to the 4th power, and then secant squared theta d theta as our dx. But now, here we have 4 secants, and here we have 2 secants, which means 2 of the secants are going to cancel out, so we will be left with 1 over secant squared theta, which is simply cosine squared theta. So this will be equal to the integral from negative pi over 2 to pi over 2, I don't know where I wrote pi over 4, of cosine squared theta d theta. But then, this integral can easily be integrated using double angle identity. So this is simply the integral from negative pi over 2 to positive pi over 2 of 1 plus cosine of 2 theta all over 2 with respect to theta. And now we will introduce a substitution, namely u equals 2 theta, which means the u equals the derivative of 2 theta is 2 d theta. But then to get our 2, we will simply divide and multiply by 2, so 1/2 times 2. This has the same effect as multiplying by 1, which has the same effect as doing absolutely nothing. So now, let's see. We have the 1/2 and the 1/2 right here combined to make 1/4. And then our bound, negative pi over 2 times 2 is negative pi. Same thing with pi over 2 we get pi out of this. And then our 2 theta will be simply our du. So we will be left with 1 plus cosine u du. And now, we can simply distribute this integral and take the entire derivative of everything. So we'll get 1/4 times entire derivative of 1 is u, so u evaluated at negative pi and pi, plus the cosine of u evaluated at negative pi and pi. I mean the sine of u, But then, for the u term, we get pi minus negative pi, which is simply 2 pi. And then for this one, sine of pi is simply 0, sine of negative pi is also 0. You can verify that using the unit circle or something. And 0 minus 0 is simply 0. So 2 pi plus 0. 2 pi plus 0 is 2 pi. 2 pi over 4 is simply pi over 2. So that's a nice answer, but now let's take a look at another integral. The integral from negative infinity to positive infinity of x squared over 1 plus x squared. And as you can see, we added an x squared in the numerator, so dx. And now we will introduce the same substitution as before. So x equals tangent theta, which means dx will be secant squared theta d theta. And now our bounds will be as before, so negative pi over 2, 2 pi over 2. And then our x squared will be tangent squared theta. Our denominator will be secant to the fourth power of theta, and now dx will be secant squared of theta d theta. But then, let's see. The secant squared over secant fourth will simplify to be cosine squared of theta, as we found out earlier. And tangent squared times cosine squared is simply sine squared, so this is the integral from negative pi over 2 to pi over 2 of sine squared theta d theta. But then we can integrate this as before using the doubling co-identity, so integral from negative pi over 2 to positive pi over 2 of 1 minus cosine 2 theta all over 2 with respect to theta. But then we can, as before, introduce the substitution u equals to theta, which means du will be 2 d theta. As before, to get our 2, we will divide and multiply by 2. So then the 1/2 will combine to be 1/4, and our bounds will go from negative pi to pi because of our substitution. And now we will get 1 minus cosine u du. But then, as we did before, we can distribute this integral sign. So we get 1/4 times antiderivative of u of 1 is u, evaluated at negative pi and pi, minus the antiderivative of cosine is sine. Sine u evaluated at negative pi and pi. But then, as before, pi minus negative pi is 2 pi, so 1/4 times 2 pi plus. But then, this term is the same as this term, which is 0, so this is 2 pi minus 0. 2 pi minus 0 is simply 2 pi. 2 pi over 4 is also pi over 2. And this is exactly the same answer as this, which means these two integrals are equal, which means the area under these functions over the entire domain is also the same. This is crazy because I don't think they differ by a constant. Tell me in the comments if I'm not mistaken. And these are really similar. You just change the one for an expression in the numerator and it doesn't change the result. And as the corollary I was talking about before, this integral from negative pi over 2 to pi over 2 of cosine squared theta is equal to this integral, and this integral from negative pi over 2 to pi over 2 of sine squared theta d theta is equal to this integral. And since these two integrals are equal to pi over 2 by the transitivity of the equivalence relationship, we get that these two integrals are equal, which means that the integral from negative pi over 2 to pi over 2 of cosine squared theta d theta is equal to the integral from negative pi over 2 to pi over 2 of sine squared theta d theta. And this can easily be verified by taking a look at the graphs. Yes, proved by graph. We have reached a new level of mathematical and rigorousness on this channel. So let's see, this is pi over 2, negative pi over 2. This is going to be pi over 2, and this is going to be 1. So then, our cosine squared graph will look a bit like this. Yeah. And our sine squared graph will look a bit like this. Wait a second. Okay. So then, this shape is the same as this shape, which means if shapes are the same, they will have an equal area. And since these two functions are even, they will be symmetric about the y-axis, which means this is equal to this is equal to this, and everything is going to be equal to everything. But wait, this equality with these two integrals gets even crazier when we introduce another integral. But first, let's erase the board. I have yet to learn how to snap my fingers. Just okay. Okay, so it worked, I guess. So as we found before, these two integrals are equal, but as I said, we can easily introduce another member to this inequality. And that member will be dun, 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 the integral from negative infinity to positive infinity of 1 over 2 times 1 plus x squared dx. Yes, by moving the exponent, the 2 as the exponent up front, we don't change the result, and here's why. That integral, if we factor out the 1/2, we get 1/2 integral from negative infinity to positive infinity of 1 over 1 plus x squared dx. But 1 over 1 plus x squared is just the derivative of the arctangent, so this will be 1 over 2 integral from negative infinity to positive infinity. Wait, not the integral we already have for our entire derivative. Where am I writing an integral sign? So arctan x evaluated at negative infinity and positive infinity. But then as x goes to infinity, arctan x tends towards pi over 2, and if we go in the opposite direction, since arctangent is a non-function, we get that this will approach negative pi over 2, so we get 1 over 2 times pi over 2 minus negative pi over 2. But then pi over 2 plus minus negative pi over 2 is pi, and pi times 1/2 is pi over 2. So all these integrals are equal to pi over 2. This is really weird because the integrals are so similar, because here we just added an exponent in the numerator, and here we moved the exponent on front. And these probably don't differ by a constant, and they converge, which is pretty impressive for an improper integral, and they converge to a really nice value, pi over 2. And yeah, this is really weird because if you take a look at the graph, which we will do shortly, you can see that this and this, these two are bell curves, but not this. And since those bell curves are not the same shape, it might be intuitive to think that they don't have the same area, but they do. And let's see about that. So yeah, this is a pretty interesting inequality, and yeah, pretty nice inequality overall. And as always, this is the end of the video. Thank you guys for watching. If you like this video, give a like, share, and subscribe, and I'll see you in the next video. Bye.